Now for some stoichiometry problems, and these are solved kind of just the way we solve for stoichiometry, except now we have to use the gas law, okay, which is PV is equal to nRT, but otherwise the setup is pretty much the same. Okay, so let's start with the first one, and the question is, what volume in liters of carbon dioxide can be consumed at STP by 525 grams of sodium oxide? Okay, and so sodium oxide is 525 grams, and we are asked for liters of carbon dioxide. Now, if you were working in normal stoichiometry, as in what we did in chapter 3, you would be working with grams of carbon dioxide. But now we know a little bit better, and so we are working with gases. Okay, so this is our equation that's given to us. The first thing we do is make sure that our equation is balanced, which it is not. So let's go ahead and balance this out. Na2 and 2, and oxygen is not balanced. So 2 here, so then 2 here, and then we have 2 carbons, so 2 carbons over here. I think that should balance it out. 4 oxygens, 4, 6, 4, yeah. Okay, so all balanced out. Now for the information that we need, so PV is equal to nRT. So the question is about what volume in liters of carbon dioxide can be consumed. All right, so if this is the equation we have to use to find liters, we first need to find the number of moles. Okay, so that's our unknown factor. All right, pressure we know, because at STP the pressure is 1 atmosphere. Volume is what we are calculating for. Number of moles we can find from stoichiometry using the equation. R is gas constant, and the temperature is given to us, which is T, okay, STP, and that is 0 degrees Celsius, and that is 273 Kelvin. Okay, so what we need to do then is start with the information given to us, which is 525 grams of sodium oxide. Convert that into moles. So 1 mole of sodium oxide has 77.98 grams of Na2O2. Again, this is coming from the periodic table, nothing fancy over here. So this gives us the moles of sodium oxide, and then we find the mole ratio. Okay, so 2 moles of sodium oxide gives us 2 moles of carbon dioxide. All right, so then our number of moles here after doing the calculation is 6.73 moles. All right, so that's the N, the unknown factor, okay, that we had. So PV is equal to nRT. We are calculating for V, which means that nRT over P is going to be our setup. And now N is 6.73 moles. R is 0.0821 liters atmosphere mole Kelvin. Temperature is 273 Kelvin, and then all of this is divided by pressure, which is 1 atmosphere, but we should still write it out. Okay, so even though we're not going to put that in our calculator, so cross out the units. Atmosphere, atmosphere, mole, mole, Kelvin, Kelvin is gone. We're left with liters over here. Our final answer for this one is 150.9 liters. Okay, and so convert that into the right significant figures. 151 liters of carbon dioxide. Now, if you were doing this using the normal stoichiometry, which is the gram stoichiometry, then you would have converted 6.73 moles into grams. Okay, that's what you would have done. But since we are working with gas laws, you need to use PV is equal to nRT, the ideal gas law. Okay, let's take another problem now. And in this case, the question is, calculate the amount of sodium azide, NaN3, needed to produce enough gas for a 125 liter airbag at 1 atmospheric pressure and 25 degrees Celsius. Okay, and so the equation given to us is NaN3 to give sodium and 3N2. Let's balance that out. 2 there. Okay, solid solid, and the gas is nitrogen over here. This, by the way, is the reaction that goes on in airbags in cars. Okay, so the gas that is produced from sodium azide is nitrogen, which is perfect for us because it doesn't harm us. Okay, that much. So the question is, calculate the amount of sodium azide. So which means we need the grams of sodium azide over here, because that's a solid, needed to produce enough gas for a 125 liter airbag. So which means that the volume of nitrogen is 125 liters, okay, because the volume of the container is the volume of the gas. And then of course we have the pressure given to us and the temperature given to us, okay. This is kind of the reverse of what we did in problem number 1. Okay, in problem number 1, we started with stoichiometry first to get the moles, but now we need to actually use the PV is equal to nRT, the ideal gas law, to get the number of moles. Okay, so it's just two opposite kind of problems, okay, or different approaches. So we still need to find the number of moles, okay, to get to the moles or the grams of sodium azide. Okay, so N is equal to PV over RT. So pressure is 1 atmosphere, the volume is 125 liters, R is 0.0821 liters, atmosphere mole over mole Kelvin, times temperature, which is 25 plus 273, yeah, 298. You wonder why they don't do that all the time, but still have to do that, 298 Kelvin. Okay, and so cross out the units. And after a while, hopefully you'll get comfortable enough to know that if you set the problem up correctly, then you don't have to worry about units so much. Okay, so initially you should write it out though. So now we get 5.109 moles, and this is the moles of nitrogen, okay, in 125 liters of nitrogen. So once we know the moles of nitrogen, now we can find out the moles of sodium azide, and then grams of sodium azide. So now using the mole ratio, moles of nitrogen to moles of sodium azide, and moles of nitrogen is 3 and the moles of sodium azide is 2, and then convert the moles of sodium azide to grams of sodium azide, and the grams is 65.02, and this is equal to then 221.5 grams of sodium azide, which if you want you can go ahead and round that off to 3 significant figures, 222 grams of sodium azide. Okay, that's our final answer. So those two problems are have a different approach, okay, when you start solving them.